All right, this recording will go through how to do the second part of the assignment for this week called beta decay, FetLab beta decay. So I'm going to start presenting my screen. All right, so if we go to the assignment here, it's called the FetLab beta decay. So we're going to explain the beta decay processes, complete radioactive decay equations, and analyze the rate of radioactive decay by applying the FET beta decay simulation. You can find the simulation on there, but again, it really only works with computers that can run Java. So you could just watch this video of me going through it instead of doing it on your own. So we're going to start with a single atom. It says, observe beta minus decay of hydrogen-3 and carbon-14. After each decay, press the reset nucleus button to watch the process again. And then you're going to write a description of what that decay looks like. So we're going to go to this. This is the hydrogen-3. If you look up here, it's really hard to see, but the grays are the neutrons, the reds are the protons. The blue ones that come off are going to be electrons, and then the small green ones are going to be called antineutrinos. We are not going to worry about the antineutrinos, so just focus on the electrons for now that are coming off. So here we go. We're going to start it. All right, and there it shoots off, and you can see that these kind of slow down. They're not moving as much anymore, so we're going to reset. Okay, so you can see that the blue one went up. There's a green one that went opposite direction. That's the antineutrino we're not going to worry about, but you can see the blue one goes up there. Okay, we'll do this a couple times. Okay, you saw that one. Here's another one. So notice the speed of these things as they're jostling around. And then eventually, after, in this case, it looks like over 40 years, 50 years, 60, there it goes. All right, now I'm going to do carbon-14 as well. So here's carbon-14. It's moving around. There it goes. It beta decays. So the blue shoots away, the green shoots a different way. This one, you can see it takes 6,000 years. Okay, so 6,000 years. Let me reset. Wow, this one's taking a really long time. All right, 24,000 years. We'll do it again. All right, so notice now nitrogen-14, carbon-14 turned into nitrogen-14 because the electron shot away. And notice they're moving slower, and nitrogen-14 will stay here forever. It will not ever decay. So it's a stable nucleus. So let's go back over here. So you can kind of describe the process, what's happening, name the two particles ejected. So we just talked about that. The antineutrino is one of them, the electron's the other. Now, why does carbon-14 decay but not nitrogen-14? It has to do with the numbers of protons and neutrons in there. So maybe actually parts 4 through 6 will kind of help us here. Because if you remember what beta decay included, also there's that P table you can use if you need to. So let's look what happens to hydrogen-3. Hydrogen-3 has a mass of 3, that's the top number, and one proton, that's what makes it hydrogen. Now during beta minus decay, what happens is the neutron turns into a proton and shoots off that electron. So as a neutron turns into a proton, the 3 stays the same because a neutron and proton have the same mass. So if one turns into the other, the mass doesn't actually change. But when it turns into a proton, it does gain another proton in that sense, right? And then that changes what type of molecule it is, or sorry, what type of atom it is. So because it now has 2 protons, we call it hydrogen or helium. So hydrogen turns into helium, and then it shoots off this beta particle, or which is a high energy electron. So we can use this symbol. So it's got a mass of 0 because it's an electron, it's very tiny. has a charge of -1, and we can just call it B for beta particle, or you can call it E for electron, okay? Now, let's talk about what happens to carbon-14. So again, the top number will stay the same, 14. The bottom number, remember, is going to go up by 1 because one of those neutrons turns into a proton. So it's going to go up by 1 to a 7. And then we'll have to go to P table here to see what 7 is. So we look over here. That would be turning into nitrogen, which according to the simulation makes sense, right? It turns into nitrogen 14. So we just put an N here, and then it shoots off that high energy electron called the beta particle. Okay, you can do cesium by yourself here. So cesium-137 is going to turn into something due to beta decay. So maybe there you can kind of talk, we can see it really has to do with that ratio of numbers of protons and neutrons. You can also look up this question if you want online and maybe get a better idea of what's happening there. All right, so moving on in the simulation here. Now we're going to count the daughter nuclei, the decayed nuclei in a 5-year span. And we're going to ultimately calculate the decay rate. I'll talk about that in a minute here. We're going to click on multiple atoms tab using 99 custom nucleus with a half-life of 5 years to gather data. So I'm going to stop it at these points, 5, 10, 15, 20, and 25. And we are going to do the kind of the lab with it. So we're going to go ultimate multiple atoms. It said to use a custom. We're going to move the half-life to about 5 years, which seems to be about there. And I'm going to use 99 of them. So I'm going to add 100 of these, 10, 20, 30, 40. Oops, hold on. Let me reset them all. Sorry. I'm going to do this over again here. So custom, half-life of 5. I'm going to pause it first. I'm going to add 100 now. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So that should be about 99 or 100. I'm going to hit play here, and I'm going to pause it at 5, 10, 15, 20, and 25. So here we go. And about there. Okay. So now what's happening is these light blue ones, these baby blue ones, are decaying into more stable black ones. Now we don't know, it's a random atom. We don't really know what it is, but it follows this kind of half-life curve that we were talking about before. So you can see how many daughters or stable ones, there are 48 left. So we're going to go back to here and we're going to type in 48. Now, decay rate would be decayed nuclei per year. So we're going to take that 48 and we're going to divide it by 5 years, and the answer is 9.6 nuclei per year. Okay, so that's how many are decaying every year on average. All right, now let's go to 10 years and see. And about there. Okay, so now we have 75 that have decayed. So we're going to go over here. We're at 75. And now we do 75 divided by 10 years now. 75 divided by 10, and that gives us 7.5 nuclei per year. So notice the rate has gone down now on average. Now let's do 15 years. And pause right there. Now we have 89 that have decayed and only 10 left. So we'll 89. We'll do 89 divided by 15, and we'll find it's 5.9. So again, K rate's going down over time here because basically there's just not as much, not as many atoms that are decaying later on, right? Most of them happen before the first half-life there. Okay, now let's go to 20 years. There, 94. 94 divided by 20, 4.7. Okay, and last one to 25. About there. 95 now. 95 divided by 25 is 3.8. All right, so you can kind of see what's happening to the decay rate here over time. It's a very similar experiment as we did in the alpha decay part. So describe what happens here. Use the values to justify writing. So it's like a CER. Claim is what's happening. Evidence would be your numbers. Now, why that is, maybe you can kind of figure it out. That would be your reasoning. But now let's go to the next part here. So part 9 here. We're going to do a new trial. We're going to do 3 different trials of the same thing. And you're going to average the beta minus decay rate. So let's get all these numbers first. So I'm going to restart. $10, $20, $30, $40, $50, $60, $70, $80, $90, $100. Okay. Okay. 53 have decayed. All right. 10 years there. 78. All right, after 15 years, it's 88. Okay, 20 years is 97. All right, and all of them decayed, so 99 is after 25 years. All right, now let's do it again, trial 2. Reset all nuclei here. $47 after 5 years. Okay, let's go to 10 years. All right, now it's 76. Okay, I'm gonna not write these numbers in anymore, so you can write them in yourself, but here we go to 15 years. All right, 86 have decayed. There are 86 daughters now. All right, let's pause at 20. We have 90 that have decayed. And pausing at 25 years, 95 have decayed. Okay, I'm going to reset this for another trial. Okay, we have 58 that have decayed. So these numbers you should have filled out from last trial. So we're on a new trial, 58, after 10 years. We'll pause for 10 years. There, we have 83. Wow, this is a lot. So it's a lot more. All right, now we'll do the rest. You can write them in. Let's pause at 15 years. Right now, so we have 87 have decayed. Now we'll go to 20 years. All right, 96 have decayed. All right, 25, all of them, 99 have decayed. All right, now I'll show you how to do the average. So what we're going to do is we're going to add up these three first. We'll add up the row first. So 53 plus 47 plus 58. I got 158. Now we're going to divide by 3 to get the average, then divide by 5 to get the average decay rate, which in this case is 10.5333. Repeating. All right, now let's do this row. So we add them all up. So 78 plus 76 plus 83 equals 237. We're going to divide by 3 to find the average, then divide by 10 to find the rate, which in this case is 7.9. All right, now you should have three numbers here. You add them up, divide by 3, divide by 15, add these numbers up, divide by 3, divide by 20, and then these three numbers, add them up, divide by 3, divide by 25, and then you'll have all these three filled out. And so you should see somewhat similar numbers to what we have up here. We're just averaging the trials to get more accurate data. All right, now using Google Sheets to create a graph. Well, we did that last time, so we can go ahead and just do it again. We're only graphing the average. So I'm going to go to sheets.google.com. We're going to add a new sheet, and we're going to copy in our data here. So we only need the average. So we just need, so we're going to copy these in. We only need this row, which is the average, and the time. So you can highlight them in copy over here, and then highlight the averages, copy and place over here. So now I have them next together. I highlight all the data by clicking, holding, and dragging. And now I'm going to click the Insert Chart button over here. And if it does a column chart, we want to make it a line chart. So there's my line chart. Yours will look different. It should have all the numbers in there. So that way it's a little bit clear. So you can see here that on our x-axis, we have the time, the years. So after 5 years, 10, 15, 20, 25. And then on our y-axis, it's the rate. So you can see clearly the rate is going down. There will be some sort of sweep in it, hopefully, as you have your data. So we're going to just Control C, and then go over here and do Control V to paste it in there. We're just going to paste it unlinked. And there's your graph that you're going to have in there. And then you're going to share and discuss the curve of your graph with another student in class. I'm going to post a question on Google Classroom that you can kind of comment on. And then you can look up how is beta decay used in the real world. And that will be the assignment for this week. So again, you can type it directly into here, or you can draw it out on a piece of paper, write it out on a piece of paper, and take a picture and send that to me. And that way I'll have your assignment. All right, thanks for watching. And if you do want to redo any of their summative assignments, let me know.